Hey folks, Mr. Myers here today. Hope you all are doing fantastic. We're going to look at LeChatelier's principle here and provide some examples of what exactly we're talking about. But here we go. So when we have an equilibrium, where it's a reversible reaction, there's this concept called LeChatelier's principle, such that when a stress is applied, which it says here, so when a stress is applied to a system at equilibrium, the system will respond by shifting the reaction rate to reestablish equilibrium. Okay, so I'll give you a second to jot that down as I talk through it again. The idea is we have an equilibrium, so like A going to B. Okay, that's our equilibrium. And if we apply a stress, the system responds so that we get back to equilibrium because we've offset it some way and it doesn't like to be bothered. And so we have to allow it to respond to go back to equilibrium. So there's these concepts right here in the second bullet point. The idea that if we add something, we're going to shift away from that side. And if we take out something, we're going to shift toward it to replenish it. In class last, I gave an example where if you're working retail or working in a restaurant and you run out of some material in stock, so you run out of a part or you run out of a food item, the tendency, because you've used it up or you've taken it out of inventory, is to replenish it, to order more. And so we would shift towards that because we want to replenish. We want to get back to equilibrium. On the other hand, if you have someone that is returning a good, like you're working retail and they return a shirt, well, then your premise might be to offer it on sale for a discounted rate or something so that you can try to sell it quickly again because you had a certain amount in inventory and now you've offset that. We've applied a stress, and so we have to overcome that. So this add away and take out toward. So what I'm going to show you here, I'm going to jot this down on separate paper here in a moment with the hover cam. But with LeChatelier's principle, we're going to discuss the effect of what it means to add components, which we said when we add, we shift away. And if we remove a component, so as add, if we remove a component, we're going to shift toward that side. It says toward, kind of written with the mouse, kind of bad. When we talk about pressure change, what effect does pressure have? And we'll also see, in Chem 1, we might have talked about gas laws a little bit, pressure against volume. And we may at the end of Chem 2 if there's time. But pressure, and we'll also talk about it in context of volume. Pressure and volume we'll see are inversely related. And then temperature change. Specifically, if we are exothermic or endothermic, which is something we learn about in Chem 1, and we'll do a lot more of here next month in Chem 2. And then what effect does a catalyst have, and what does a catalyst do? What is a catalyst? So I'm going to switch over to Notepad, and we're going to talk about these things. Yeah, I'll keep those for now. All right, so one of the first things we have, let's say we're looking at this equilibrium for the moment. So we have H2 as a gas and iodine as a gas in equilibrium, making 2HI, which is hydroiodic acid. All right, so this is our equilibrium. And when we talk about adding and removing, really we're talking about concentration. So concentration, okay, represented by the brackets here. So if we add concentration, we shift away. And if we remove concentration, we want to replenish it. So we shift toward the thing that we're removing. Okay, so for example, let's say that we go to add iodine. Is the equilibrium going to shift to the right, or is it going to shift to the left? In other words, will it shift toward the products or toward the reactants? Hopefully, you said to the products is a reactant. So if we're adding something on the left side, we're going to shift to the other side, to the products. So we're going to shift to the right. What if we said remove HI? Hopefully you said it would shift toward the right because HI is on the product side, and if we remove it, we want to replenish it. So we'll shift to the right. What if we remove H2, hydrogen gas? Hydrogen gas here is a reactant, and if we remove, we shift towards it. So we're going to shift to the left to recover or replenish that which is taken out. Okay, so that's the idea of concentration. Adding, we shift away. Remove, we shift toward. Okay, for my next example, we're going to do things a little out of order here, but we're going to focus on temperature. Okay, temperature, which for our sake will also represent as heat, because temperature is a measure of heat. Sorry about that.
Hey, Shay Tucker, if you're here in the building, come on down to the main office. Shay Tucker, if you are in the building, swing on over to the main office. Thanks.
All right, so temperature is the idea of heat. So when we discuss if we add versus remove, okay, so add versus remove. Well, we also have to look at this in the context of if something is exothermic or endothermic. Recall that if something is exothermic, that we are releasing energy. And so typically, well, not typically, always, if it's exothermic, energy or heat is on the product side. And if you have something that's endothermic, that's going to be absorbing energy overall, which means it's going to be on the reactant side. So here is an example equation. Let's say we take nitrogen gas plus 3 equivalents of hydrogen gas which makes 2 equivalents of ammonia gas plus heat. Okay, so here we will be able to describe this reaction specifically as exothermic because heat is on the product side. It is exothermic, which means in some cases instead of plus heat, we might also see this as heat not written, but delta H would be written as negative something, I don't know, kilojoules or kilojoules per mole. If it's negative, it's exothermic. If it's endothermic, delta H is positive. Okay, so this one, heat is on the product side. So the add and a remove acts much in the same way. If we add heat, which could also be thought of as increasing the temperature, Well, heat is on the product side, so if we add heat, we're going to shift away. So it's going to shift toward the reactants to the left. If we remove heat, which would be like decreasing the temperature, or measured by a decrease in the temp. Well, if I remove something, I'm going to shift toward it. Since it's on the product side, we're going to shift to the right onto that side. So we'd shift over there. Okay, depending on the problem that you have, it'll either be written something like this, where they tell you the value and sign of delta H, and it's up to you to figure out if it's endo or exothermic. And if it's exothermic, you know, we're product side. If it's endothermic, we're reactant side. And then you can decide, are you adding or removing? Are you increasing temp or adding heat, decreasing temp or removing heat? Okay. The next thing that we're going to look at here is pressure. All right, pressures can be a little bit trickier, but something to keep in mind is that pressure and thereby volume, which I'll get to in a moment, pressure will only apply to gases. So if you have an equilibrium that has something that's aqueous, we don't count it for the sake of the effect of pressure. So I'm going to use the same equation we used up here above, and I'll rewrite it. N2 gas plus 3 hydrogens gives us 2 ammonia plus heat. The heat's not going to have any role here with the pressure component, but we're still including it, so you're used to it. And in order to determine what effect pressure has on this equilibrium system, what we look for is the side with more moles of gas. Okay, we're going to look for the side with more moles of gas, i.e. looking at the coefficient, and that side is going to be affected by the pressure. So let's count. How many moles of gas are present on the reactant side? Hopefully we say 4. 1 here plus 3 moles of gas there, counting the coefficients. So we have 4 moles on the left, and on the right side we have 2. Okay, that means the side with more moles of gas will be affected by whatever we do. So in this case, we look at that side. If we say, hey, let's increase the pressure. So an increase of pressure is going to shift from this side. It's going to shift away because we're adding pressure. So pressure will go away and shift to the products, to the right. Okay. If we decrease the pressure of the system, then we are lowering kind of the relationship it has with the amount of moles. And so if we lower the pressure, then we're going to be removing moles of gas in that way. And so we'd shift to the left, to the reactants. Okay, and as I mentioned before, volume is inversely related to pressure. Of pressure. Okay, you might have an example where they say, hey, the volume is increased. I always find it better and easier to work with if we say, well, pressure and volume are opposite. So if, you know, we have an increase in volume, well, really that's a decrease in pressure. And so I still look for the side with more moles of gas, and I say, okay, so I'm really looking for a decrease in pressure. So I'm removing moles of gas. It's going to shift to the left. Okay, so in this example, it would shift to the left based on that. Okay, one last item. is the effect of catalysts. Most of you probably know what a catalyst is by now. It is a substance that speeds up a reaction without getting used up. Okay, so it doesn't get used up, and it's going to speed up the reaction. Well, as it turns out, the effect on equilibrium is none, no effect. And think about it. We've already said that the rate forward in equilibrium is equal to the rate going in reverse. So if you're speeding up a reaction, you're changing the rate, and at equilibrium, the rate forward and the rate reverse are the same. So if that's the case, then catalyst will have no effect on the equilibrium. So it's not going to shift in any direction whether you put in a catalyst. It'll just make the process go faster. Okay, and that is it for LeChatelier's principle. Have a good one.